basically the idea that hot water will freeze faster than cold water.
And how did this come about?
Has kind of been around for a really long time. So Aristotle, there are writings from Aristotle about it that kind of talk about how fishermen, ice fishermen, used to cut a hole in the ice and then stick their reed into the ice, and then they would pour hot water around that reed so that it would freeze in place. It's named the Mpemba effect after a actual high school student who is from Tanzania, and his class was making ice cream. Um, and when you make ice cream, you kind of boil water and milk and sugar together, and you have this boiling mixture that you then need to freeze. So he wanted to get his in the freezer as fast as he could so that it would be frozen by the time that he needed it. So all his classmates kind of waited for their boiling mixtures to cool down before putting them in the freezer, whereas Erasto Mpemba took his boiling milk mixture and put it right into the freezer. And when they opened the freezer and they kind of or they got their ice cream out of the freezer, his was frozen and everyone else's was still liquid. So he was like, how does this happen? And he teamed up with someone from a university nearby, and they ended up writing a full scientific paper about it.
So what is the science behind this? Because logistically, this makes no sense.
Mm-hmm. Yeah, no, it's totally counterintuitive, and that's what makes it so interesting. Um, I would say for the science behind it, it's easier to explain if instead of looking at water, we look at like one single particle by itself. So water has a phase transition between the liquid and the ice, and that makes it scientifically really complicated to look at. Because like ice has all these crystals, and the crystals kind of encourage more crystals to form. So turning from a liquid to an ice can depend on what container you're in and what environment you're in. Whereas if you just look at a single particle, you kind of get rid of all of those complications. So the Mpemba effect has been proven in single particles kind of over and over again. So the idea is that you take one little particle and you put it in a potential well. So if you think of like a typical water well, if you imagine you fall into a well, you're most likely going to be at the bottom of the well. If you're trying to climb up the sides of the well, it takes more and more energy to get up the side of the well. So you're climbing, and it's like your arms are tired. It takes energy to get up there. So most likely you're going to fall back down to the bottom of the well. So if you release a particle in what's called a potential well, most likely it wants to end up at the bottom of that well. And you can model water using two wells put together. So one well is the liquid and one is the solid. And the solid, it requires less energy for the particle to be in a solid ice state. So it wants to be in the deeper well that represents ice, rather than a shallower well that represents water. So if you release a particle and it has a bunch of energy to start with, which means it has a higher temperature, it's actually more likely to fall into the deeper solid well than if you release a particle with less starting energy, which is more likely to kind of fall into the liquid well and then slowly turn into ice. So really the Mpemba effect is saying that if you start with more energy in your particle, you can skip around more and you'll more quickly fall into that solid ice well.
Interesting. So this has been proven over and over again. This is a real effect. Does it happen in the opposite? So if I'm going to boil water on my stove, should I fill the pot with cold water or hot water?
So it does happen in the opposite direction. That kind of idea has been proven relatively recently with the single particle experiment. It's a little bit less noticeable in the reverse direction. So there's kind of this second time stage in between these two wells that I was talking about. And when you go in the opposite direction, there's a little bit less of a difference. So you don't see it quite as strongly. So I mean, if you want to boil some cold water, it might be a little bit faster, but in reality, it's probably not going to be something you'd actually notice. There have been cases where like the hot water pipes in people's homes are more likely to freeze than their cold water pipes.
So is anybody doing research on this now, or is this just kind of like, okay, we accept this for what it is? Or are there stubborn scientists out there that are trying to disprove this?
No, it's actually still fairly controversial, especially in water. So these particle experiments are like pretty well accepted, but because of that phase transition in water, all of the experiments are like really hard to replicate. So people are doing those kind of experiments right now, especially in accounting for that phase transition. And then there are groups who are doing experiments with like liquid metals and different materials to see the Mpemba effect outside of just water as well.
So if there is another deep freeze, say in some part of the country, should people take their pots of boiling water outside and throw them, or should they throw cold water?
I think it'll probably work either way.